welcome to another episode of Rustacean Station. I have my guest Stephen Crane on, who is the CTO of Imminent, who is working on C2Rust, which is a transpiler from C, C++ code over to Rust. There's no C++ yet, right? Just only C, I think. Maybe I spoke too wrong.
No C++ yet. Yeah. Thanks, Owen. Happy to be here. Happy to talk about the project. Yeah, C2Rust is a project that transpiles C into Rust. You got it.
Now, I think there's a lot of people in all communities that look at this, I don't know if you call it a fad, or it's always this kind of thing like, let's rewrite it in Rust, right? These Rust fanboys. I mean, is there some...
The Rust evangelism strike force is out in force.
Yeah, is there some relation to this? Are you guys just Rust fanatics and just think Rust is better, so you want to do this kind of thing? Or is there actual real need for this?
No, we love Rust. I mean, that's kind of why we got into Rust and doing things with C2Rust. But sort of the background of C2Rust is we were looking around at all of the legacy code floating around, all legacy C code in particular, and wanted tooling that would take that legacy C code and provide a starting point for rewriting things in Rust. It's not for everything. Not every project is a good fit for that. But for the projects that you really do want a safe Rust implementation, you've got a good C code base, C2Rust is a project about providing that starting point. And then from there, you can rewrite, refactor, and bring it into nice Rust, let's say.
Yeah, that's always the tricky part with these kind of transpilers, in my opinion, is like, how do you take something from one language into another? And if you're just taking one thing to another and then like compiling that and actually looking or tweaking it, it's fine. But once you start to look at it and you're like, is that really what I want? Like, I used to work with Dreamweaver a long time ago, before I even became a professional programmer, or I still feel weird saying that. Before I was getting paid to write code, let's say it like that.
Fair.
I look at the HTML like it's generated, and it's even at that time, I was like, wow, this is super ugly, it makes no sense. And imagine trying to change all that by hand later. But you guys are actually trying to go from C to Rust, but not just Rust, but stuff that actually somewhat makes sense. And of course, I think I've seen some articles saying that you guys do have some problems with making that actually happen, which makes sense.
Oh yeah. I mean, C is a really good fit for transpiling into Rust. It's the feature set of C and the feature set of Rust is close enough that we can sort of do a one-to-one translation. It's probably important as a little bit of background on C2Rust is exactly how it works. We take a C code base that you can compile with Clang. We run that through Clang, and then we transform that into unsafe Rust. That's our starting point. And from there, we want to have something that you can then refactor, possibly with more tools, into a workable, readable, ergonomic Rust codebase. But the starting point for that is a one-to-one unsafe Rust translation. So if you have a pointer in C, you have a pointer in Rust. That looks pretty ugly. Unfortunately, there's not always clear Rust equivalents for C things. And when there are equivalents, they often aren't the ergonomic way of doing things. Raw pointers are a perfect example of that. If you want to offset a raw pointer in Rust, that's a long expression. If you want to offset a raw pointer in C, you just add to it. So C2Rust does some work to make that a little more readable for you. Things like array accesses are actually made into Rust array accesses when we can. Can't always do that. Unfortunately, C does strange things with arrays that Rust, of course, doesn't let you do. But when we can, we try to make it as close to what a human would have come up with. That said, there's a long way to go. We definitely have low-hanging fruit there. Macros are a particularly interesting thing we can get into later. But the goal is very much to have a readable starting point, or at least a human readable and transformable starting point, even if it is ugly. We're not targeting machine readable output. Many transpilers target sort of just machine code, like you were saying, from Dreamweaver to HTML, or in the programming language space, I don't know if you've heard of Emscripten. That was the predecessor to WASM, where it takes C code and spits out JavaScript that's equivalent, but is completely unreadable. That JavaScript code is, no human would ever look at that and go, I can definitely work with this. We have sort of a different goal with C2Rust. We're after something that a human can look at, go, yeah, okay, it's ugly, but I can fix this. It's a starting point.
Yeah, I'm still trying to understand this, how this actually works. Like, what I understand about LLVM, maybe this is also good for people at home, right? Is that because you're basically, I mean, obviously you have to use LLVM kind of stuff because you're using Clang, which is for LLVM.
Yeah.
So you stick C code. So what I understand what really works is like you stick your code in the front end. It goes to some kind of intermediate language, which is LLVM language. I don't know what the name is called, but it could be the
We
name.
actually, there's,
There's another step in
I
between.
can sort of explain that pipeline.
Oh, I'm sure. Can we talk about what is? How about this? Because I'm sure you know this more than me. Can you explain what the typical process is where we go from code to machine code, like basically the binary, and then
Yeah.
talk about where you guys kind of inject stuff? Because I find it really weird. But how did this like? Can you actually go backwards from this intermediate code to where you went? That's what sounds like what you're doing.
No, that would be hard. You might be
That's why
able
I'm
to
so
do
lost
that,
about
but
how this works. Yeah.
yeah, that's actually how Emscripten works. Emscripten, not C2Rust, but the C to JavaScript transpiler predates it. That actually takes C code, parses it through Clang. So a normal compiler has a front end, a parser, that parses your human readable source code, and it generates something called an AST. An AST is an abstract syntax tree. And this is really just a computer readable graph representation of your program, your source code. It's one-to-one correspondence from the AST directly to the source code, generally speaking, in most compilers. Rust compilers this way, Clang, which C and C++ for LLVM is this way. And then there's a series of passes that take that AST and transform it, in LLVM's case, Clang's case, into LLVM IR. This is an intermediate representation that's sort of language and machine agnostic. It aims to be something in between the front-end language, C or Fortran or various other. Rust, for example, is an LLVM, uses LLVMR. And then you've got this middle thing called IR. That's an abstract machine, if you will. It's a sort of a virtual machine that has infinite registers. It has a memory space that is sort of unconstrained. It abstracts all of the machine details away. And then you have various transformation passes on that in a normal compiler. These transformation passes are optimization passes. Generally, you go from LVMIR into static single assignment form, which is different form of IR. It's the same IR, just a different form of it. And then you transform that into something specific to the machine you're working on. So x86 or ARM. There may be another machine level IR in here. Some compilers use that. And then you spit out, after probably some more optimization passes, there's a lot of them, you spit out machine code. You spit out x86 assembly or just raw bytes or ARM or WebAssembly is a backend for LLVM. So you can compile your Rust code into LLVM-IR, which then compiles into WebAssembly. For a transpiler, it's a little bit different. And specifically for the transpiler we want to do, it's quite a bit different. A normal compiler sort of wants to optimize things as much as possible. We're after something different. We're optimizing for readability and correctness first. We want to make sure your code works the same as it always did in C. But then we want to, as much as we can, optimize for readability. So rather than going through that whole compiler pipeline and getting something very, very far from the source code, we actually interpose right at the front end. So the Clang parser parses your C code. It's a standard parser, and then generates that abstract syntax tree, that tree representation of the C source code. We grab it right there. So C2Rust actually has some C++ code that links against the Clang, the libclang tooling libraries. I believe it's called libtooling. It's the C++ bindings for Clang. And we actually dump the entire AST at that point into our own representation. We actually use SERD to serialize that abstract syntax tree into, I think, bin code. Don't quote me on that. I would have to go look at the source code. It's been a long time. So we have this very thin C++ layer that serializes into, I think it's bin code, this abstract syntax tree. And then we pass that buffer of serialized data over to Rust. We want to get it into Rust as soon as possible. C2Rust is written in Rust. We like working in Rust. We don't really like working in C++. So I try to work in as much Rust as we can. And We grab that abstract syntax tree. We use SERDI to deserialize it into a Rust tree representation of the abstract syntax tree. And then we do a pass over that tree. Remember, that tree is just the source code. It's pretty much equivalent to the C source code, just parsed into a machine-readable format. We then transform that C abstract syntax tree into a Rust abstract syntax tree. Rust also has an AST, and that transformation pass is where we do all of the fun things. And then once we have a Rust abstract syntax tree, we print that out as source code. We pretty print that into a file, and now you have what looks like normal Rust code, if a bit ugly.
Okay, yeah, all right, that makes sense. I forgot about the AST.
Yeah, the AST is really the key thing here,
Yeah.
because the AST is sort of the machine representation of something human readable. And we don't want to go any further than the AST. Clang has its own IR that it's transforming into LVM. We want to stay as close to the front end, the parsing, as possible, because we don't need any of the complex information from C. We don't need any of, for example, the type information, really. We don't need anything about the machine because we're not at that level yet. We just need the front end sources. So that's the way most source-to-source transpilers actually work. The transpilers that go through the entire sort of compilation pipeline and emit machine code are a little bit closer to an actual compiler. They're just targeting a virtual machine that happens to be another programming language. For example, C into JavaScript or Rust into WASM. It's a sort of a different process, and they're very different goals. We want to run C2Rust on your code base, maybe once or once every time there's a new imported version. But you don't want to be running this every time you compile. You want to run this and then have a refactoring phase where you adjust the source code, take out unsafe, change pointers into RC, box, these kinds of things.
Okay. Oh, that's interesting. I'm just trying to think about how that works. I mean, I kind of understand it. I mean, C itself, I guess, is not that complicated of a language, right? So it shouldn't be hard to start flipping things around for what you need, right?
Pretty
Okay.
much, your normal C constructs map pretty nicely onto Rust. I mean, Rust is
Yeah.
supposed to interface with C nicely. We mark all of our functions as extern C. They're unsafe. They use pointers. It sort of behaves the same. There is one really interesting aspect to this, though. C allows gotos. Rust does not have goto. This is the difference between what's called unstructured control flow, where you can break out of a loop using a goto. You can arbitrarily move around the function, versus structured control flow, which is what modern programming languages, including Rust, use. So when there is a gotos in your code, we have to do something really special. And it turns out that switches are a similar thing. Switches in C really are closer to gotos than we would like. They're unstructured. And so what we have to do is we have to have some way of transforming unstructured control flow from C into structured control flow in Rust. And this is possible. It turns out the author of Unstructured pioneered a really interesting algorithm to do this. It's called relooper. Alon Zakai sort of invented this thing back at Mozilla back in the day. And what it effectively does is it transforms, when you have gotos in your source code, transforms your code into a state machine. So you can think of goto labels as sort of states of the program. And you have a big loop over your entire function. And when you have a goto, instead of, doing a goto, you set a state variable and continue, go up to the top of your loop, and then jump to the other place in your function. It's really kind of ugly, but it works. This was important to go from C into JavaScript, because JavaScript is also a structured control flow language. It's well behaved, and it doesn't have gotos. So Alon invented, I think it was mostly Alon, there were some other folks that helped him on it, but invented this relooper algorithm, and we use that in C2Rust as well. But we did have to do some interesting modifications to that. We don't strictly use the relooper algorithm that described in the Unstructured white paper. We're targeting readable source code. So rather than every use of a switch or gotos being transformed into this weird loop with weird state variables that are unintelligible to humans. We want to really make this look like Rust if possible. So things like break, things like switch statement that could be made into cases in a match statement. Like, these are things that we want to transform into reasonable Rust code when possible. It's not always possible. C lets you do arbitrarily bad things. If anyone's curious of the arbitrarily bad things and has never heard of Duff's device, Duff, go Google that. You'll have fun. But we want to, when possible, make this into something nice. So we sort of hacked around on Relooper, the basic algorithm, to transform some of the extremely common cases of unstructured control flow into what you would expect in Rust. So, for example, what Relooper does is it takes every while loop, every for loop, every do while loop. All of this is condensed into just a loop structure. We then take that loop structure and say, well, we think this looks like a for loop. So we're going to make it back into a for loop that does nice iteration. Again, when it fits, this is really just sort of special cased cases where we do something that looks reasonable, that is correct, as long as we can determine that it is indeed correct.
Now, the C2Rust, I mean, are you just pointing it to certain functions, or are you saying, okay, do this whole file, or you can only say do this whole directory?
Good question. So we need to know exactly how to parse your C code. Any tool that operates on C code has to know the precise details of how it was compiled. The preprocessor in C does different things depending on what was defined in the command line and what compiler options you passed and all of these good things. So we actually use a tool standard format, I don't know what you call it, compile commands.json. So this is a pretty standard thing now in the programming language static analysis community. Clang supports this as a first class thing. But there's various tools that you can run sort of outside of your build system or over your build system to generate a JSON file that describes how to compile each C source file in your project. Basically just a JSON file with all of the compiler flags and which file we're compiling. Pretty simple. CMake will output this. Various build systems will just output this for you if you ask nicely, as well as tools like Bear sort of wrap a make build system and generate this JSON file for us. We then parse that JSON file. Well, Clang actually parses that JSON file built into Clang, knows how to compile each C source code file. And then we have command line options for C2Rust that says, well, if you want to just run over the entire thing, you can do that. If you want to generate Rust code for a particular C file, you can do that. But generally speaking, the easiest way to use C2Rust is run it over your entire compile commands.json. It'll take each individual C file and transform that into an equivalent Rust file. And that works pretty well. We'll even generate you a build.rs and cargo toml and this kind of thing to get a basic binary working if you pass the right flags. So you can literally go from one of these compile commands.json to a Rust project that you can cargo build, cargo run, and it just works. If your C source code is fairly standard and you're not doing any weird things, you can just cargo run and you'll have a completely unsafe Rust project that is equivalent to the C project.
Okay. You guys really do a lot of information. I guess that makes sense. Like I said, you need the compiler flags could make. I'm not too familiar with
To
compiler
do
flags,
it,
other than I know that they're sometimes required for, like, obviously I've seen like including headers or including
yep,
extra
exactly.
libraries or paths, but I guess you kind of need those because you need to say, okay, this function is calling this function. What is this function actually doing, etc. Right?
You need those just parse C code correctly. So, for example, finding headers is sometimes a problem. Your project might put headers in various directories, and C2Rust doesn't really know anything about how your C project is laid out. We don't try to divine how you build your C project. Everybody has a different build system. We're just trying to take, okay, what actually happened during the build? This is one instance of a build. This is one particular configuration. We don't support, for example, having like build flags and translating those. We don't really know anything about your build system. But you can take one particular instance of your build system that generated some binaries, and then from that, we know how to parse your C source code and what your C source code actually really corresponds to, rather than this abstract thing that has preprocessor defines all over the place and header includes that need to be resolved and all this. So yeah,
Okay.
parsing C is actually way more difficult than you'd expect. Everyone is like, yeah, parsing C is easy. C is an easy language. It turns out C is not a language that exists. It's a language that whatever compilers expect or accept people write. So if you're not using a real compiler to parse C code, you're going to have a really bad time. People do all sorts of nasty, terrible things to C. We want to support as much as we can. So that's why we're using standard tools like Clang rather than sort of our own front end. I should shout out a little bit of the history for C2Rust. One of the projects sort of inspired us kind of as we were thinking about transpiling C into Rust. Jamie Sharp wrote a really cool thing called Corrode. And Corrode is doing basically what we're doing with C2Rust. It's a transpiler from C into Rust. A few differences, though. It was written in Haskell, which as much as I love Haskell, I can't manage to actually work in Haskell for real things. And didn't use sort of Clang as the parser. It was a Haskell C parser, which is great for prototyping, and it made for really easy and very readable prototype. If you're interested, I would highly recommend going and reading Jamie's Haskell sources. They're very readable. They're sort of, he writes literate Haskell for this, which is super interesting, lots of comments. But we wanted to build something a little bit different. We wanted to build something that we could throw at hundreds of thousands of lines of C code and we'd get working Rust out at the end. And to do that, we had to start from Clang. There's really no other front-end tooling that is up to the task. GCC is a nightmare to work with. Apologies to the GCC devs out there. I love you all. Keep up the great work, but I'm not smart enough to use GCC. So we took Clang and started from that building block and then wanted to build the rest out in Rust. And so now we're at the point we're at.
Going back to parsing C, right? I'm not super familiar with how C works because when you say C, there's more than one kind of C, right? I always say like C99, C95, and CC. I don't even know all the differences, but I
Me
would think
either.
maybe 90% of it is probably about the same, but at least, right? Maybe even 99%, but there's going to be some that, I don't know, could they act different in between?
Yeah, they do act a little bit different in between, and that's part of the reason we need this compile commands with compiler flags. Those compiler flags tell the compiler how to interpret the C source code. Clang understands most of these types of C. It has various flags for, hey, this is C99, this is C89, and knows how to parse these various things for us. That's, again, one of the reasons you use like an industry well-tested front end is because C as a language is very fragmented. There's not one particular variant of the language that everyone writes. It's not like Rust where you can parse Rust 1.0 and it's the same everywhere. There's also compiler extensions, which are super interesting. Various compilers have added extensions to C over the years that aren't standardized, but they're common enough that everyone uses them. These are various attributes, various interesting things that are actually getting standardized finally. C is still a living language, still new revisions come out every once in a while. But everything that sort of Clang understands is a pretty good slice of real world C. It's not everything. There's various things that only GCC understands, there's various things that only MSVC understands. But as long as you're using one of those three big ones, you're probably in a good spot to parse 99% of C code.
Oh, yeah, this is something I've heard, and it just blows my mind. It's like, well, if you compile it with GCC, it's like this. You compile it with LLVM, it's like this. You're going to have some inconsistent behavior. It's like, is this not the same language? So why the hell is it that...
It's not. There's a great paper. I don't remember the actual title of it, which is going to bother me. But it's about C as a language not really existing. It's really just a collection of whatever the compiler will accept, people will write. And that is the definition of the C language. Rust isn't actually that far different from that, right? Rust doesn't have yet a standard, a Rust language standard. There's not a document that describes in full the Rust language that I can pick up that document using nothing else and implement a Rust compiler. That's being worked on. It's active work in the community, and I think it's great. But as it currently stands, Rust is whatever the Rust compiler will accept.
I think Ferricene is working on something because you need some
Yeah.
kind of standard when you're doing like these highly critical systems, right? Because you need to say, okay, this code works and it's going to compile it to this way, and we
Yeah.
can prove it. So it's not just
Yeah,
written down. It's like, no, we prove it, right?
exactly. There's some really awesome work being done on getting Rust to the point where it's approved for critical systems and systems like cars or airplanes. And that verification and validation work is super critical to getting Rust into these places where it really should be. We all know that Rust is safer than C. In the average programmer hands, you're going to have a lot less memory issues in Rust than in C. But what we have right now, we have C compilers that are certified as safety critical. This C compiler performs a correct translation from this C's source code to this machine code. And that's really what we need out of Rust is a certification that, like, yes, this Rust compiler, this particular version, follows this standard and produces this code. And we don't have to worry about the compiler anymore, and we worry about writing correct code.
I was wondering, like,
I'm
who
really
should be in
excited to
charge of
see where
that,
that
though?
project.
Sorry, I was just kind of curious about who should be in charge of that because it seems like something maybe Russ, what do you call it? I forgot the name of the community, right? Maybe they should be in charge of Russ. I want to say advocates. I forgot the name. The Russ Foundation.
The Rust Foundation, yeah. I mean, the Rust Foundation does, from my understanding, I don't know a ton about the foundation in particular, but they do a little bit different thing. The Rust project itself is working on a standards document. I don't know how far that standards document is at this point or when we will ever have that, but I know it's a goal for the project is to have a standard ABI, have this stuff standardized. The problem with writing down standards is you're stuck with them. So you want to get it right. And I know a lot of time and effort is being spent in getting that right. And I think getting it right as a first draft is probably a lot more important than getting something out there then has to be revised over and over
But isn't getting it wrong actually better because that will just create new standards, right?
again. Well, there's not enough standards in the world, so we definitely need more of them. And maybe we should have a standard for standards.
Isn't there like an XKCV or something? I forgot how you say that.
That's
A comic
exactly
where it's
it. Yep,
like,
yep.
oh, this
There's
is horrible,
13
and then we make
standards
a
in the
new standard.
world. Let me make one that's better than all the others. And
Yeah.
now there's 14. That's
Yeah.
really how it goes.
Yeah.
Yep. Nothing is ever perfect the first time, and nothing ever fits everyone's use cases. I'm sure when we've been building C2Rust, we've had lots of folks come by and say, hey, do you support C++? And we're like, we're a tiny little project. C++ is a really big language. No, not happening. I would love to support C++. We get this question a lot, and technically, I think it's possible. We've talked about some ways, we've talked with some folks, and C++ is a much larger gap between that language and Rust, but there's ways to bridge that gap. Unfortunately, it's also a lot harder of a language to parse and understand and translate. So it's really a lack of engineering time, and we think that the engineering time we do have to put into the project, we should spend on making it more robust, making it produce more readable output, making it safer even. But C++, CXX is probably your best bet.
It's surprising to hear that C++ is such a big language because it is plus plus. Just add one to it, but it seems like that one is not
You'd
really easy
think
to
it would be
measure.
like a small revision. Yeah, I think the standard is like 10x the size of the C standard. It's ridiculous.
Yeah.
I'm impressed that C++ keeps adding features, and some of them are really cool, but it keeps growing. So it's a moving target, and we want to stick with something we understand mostly.
From what I understand, like I think Linus is very much adamant saying like C++ is just like a really messed up language that should not be used at all, right? I mean, I heard a lot of weird stuff about what's going on in C++ with templates, and even you also have classes, and I thought they're supposed to be similar, but maybe I don't understand. I never seen a template before in my life, so
C++ is a complicated language. I think C++ is really interesting. It's the sort of amalgamation of everything. It's like the board. Keeps adding all the things for everybody. And that results in a very complicated language that fits a lot of use cases. Like a lot of people use C++ really well. Unfortunately, Nobody knows how to write C++ without memory safety errors. It's the same thing as C. The best programmers in the world write memory safety errors because you can shoot yourself in the foot. C++ is the same deal, even if you're using some of the safer constructs in it, like smart pointers. You're going to have problems. That's really why we started working on C2Rust in the first place. I come from a memory safety background. I studied how to make software more secure in grad school, this sort of mitigating memory safety errors in C and C++ so that they can't be exploited, even though they're still there because we can't find them. But let's make it harder to write exploits. Turns out that's a cat and mouse game, and I think it's an important cat and mouse game for all the code that still exists out there that we need to make safer somehow. But really, going forward, we should be using a memory safe language, whether that's Rust, whether that's Go, whether that's Swift, whether that's you take your pick, all of the memory safe alternatives out there right now. It's the way forward. And so we wanted, rather than work on more mitigations and more ways to harden your C code, C++ code against exploitation and security vulnerabilities, we really felt like the way forward is Rust. It fit the use cases we care about: high performance systems, low level software, kernels, things where you can't really have a GC, things where you can't, or at least you don't want a GC potentially, and you want full control of the machine, you've got Rust. So that's where we came from. That's how we got to C2Rust. I started a little company with some folks from grad school called Immunent 7 years ago. Wow, time flies. And we originally started out trying to add security to C and C++ by building new mitigations. Most of that was open source work, and we built some cool stuff. But in the end of the day, you build a new mitigation and it makes it a little bit harder to exploit something, and then a new security researcher or attacker will come along and figure out a way to bypass that mitigation. So you have to layer on more and more and more, and it's pretty soon you have this tall tower of mitigations that now you're paying a performance penalty on every single line of code, even if that line of code's not buggy. And there's some really cool stuff out there. There's really great CFI alternatives, control flow integrity. There's memory tagging. There's a lot of neat things that you can do in that space. We just felt that the way forward for the industry really has to be to get off of C and C++. Nobody knows how to do this right. Not even the best programmers, the best companies can write correct code. So we see the way forward as Rust, and we want to work on tooling that makes it easier to get to that world. I want to kill C. I want C to die. I don't want to ever see a line of C code in my life ever again. And of course, I see it every day. So the way forward here is to build an on-ramp onto C, or at least that's what we think.
I mean, did we ever really address that problem of, let's rewrite it in Rust, right? I think we kind of touched on it, but let me just expand that point a little bit more, right? I've heard a really good argument, and people seem to kind of also be looking at it and kind of agreeing with it, which is, okay, this piece of code or this section of code is written in C. It's been battle tested. It's been 20, 30 years, whatever, a significant amount of time. Let's not rewrite that piece because that piece is already like butter. It's smooth, right? It just works.
Mm-hmm.
I mean, C2Rust, is there a way that maybe you can exclude parts of code to say keep them as C?
Yeah. And that's...
What about that thought process too? Sorry, it's kind of multiple questions at one. Like, can we actually
No,
exclude
no,
functions from C and not convert them? Is one good question to ask, and I'm happy to hear that we have something for that. The other one too is, what do you think about that opinion?
I think there's a lot of merit to that. Every time you touch a code base, you introduce bugs. The nice thing about moving into Rust, and especially if you can get your code into entirely safe Rust, is you're probably not introducing memory safety bugs. And that's important for some use cases. Not every use case matters. I think of video games as the easiest use case where, if the video game crashes, it's probably not the end of the world. They do that all the time. It's not a security vulnerability necessarily by itself. And there's probably more important things to work on. That said, there's some code bases where a memory safety violation is a massive problem. Think about file format parsers, your audio, video, codec parsers, things like this, where if there's an issue there, that's exposed to the entire internet. And there's constant issues there. We see even the most mature codecs in FFmpeg and such keep having bugs. They're hard to fuzz, they're hard to find these issues, and they're really quite complicated pieces of code. The algorithms and the just implementation details is hard to get right, and it's harder to get right safely. So there's definitely different types of software that some is more important to get into a memory safe language than others. That said, some code bases are best left alone, and new alternatives in memory safe languages can come along someday. Or if you're writing new code, maybe you should, stop writing C and C++ and write Rust instead. But we wanted to give an option to sort of lower the barrier to entry to rewriting in Rust. Not everything should be rewritten in Rust. Not every project makes sense. And in fact, we've seen folks who looked at using C2Rust, ourselves included, and some code bases just suck. Like, some old C code bases are just poorly written, poorly architected. They grew organically into a mess. And, maybe it's best to start fresh. Starting from a transpiled version of that really old and cruddy C code that nobody really understands how it works, probably not your best starting point. But code bases that are cleaner and well structured, we find work really well, because those are the code bases where things make sense. The paradigms really do fit into what Rust expects for the most part, because the programmer team working on the project thought about this stuff ahead of time and just couldn't express all of the memory safety concepts in C, but they're implicit. So well-structured, clean code bases work well to translate. Very ugly and spaghetti messes, not so much. Well-tested and well-fuzzed code bases, probably not the thing you want to rewrite, but important codecs, important parsers, and it's probably also worth looking at when you're looking at rewriting or writing anything in Rust is where can you get the best bang for your buck? Where is the I come from a security background, so where is the most security critical parts of your code base? What are the parts that are likely to fail and likely to fail badly? And those are often parsers. They're the things that touch input from the wide world, and they're the parts that you really want to harden, whether that's through fuzzing and testing your C and C++ code very thoroughly, or possibly rewriting it in Rust. Those are the parts that where it makes sense. Other parts, not so much. It's okay. And that's one of the things that we wanted to do with C2Rust is we wanted to make a tool that could transpile your source code to C, but incrementally. So if you want to do this one function at a time, one file at a time, one module at a time, you want to mix C and Rust code into amalgamation of, you've got a parser over here that this module, and we've rewritten that in Rust and cleaned it up and made it safe. And then we have an unsafe interface between that and the rest of the project. That works. Because we're starting from a direct translation of the C code that works exactly the same. All of the function arguments are the same. All of the structures have the same layout. It's similar to BindGen in that respect. You've got an ABI layer between Rust and C that is the same. And so you can transparently mix and match as long as you're not changing those types. So if you can change internal types in a module, and this is a well-structured module that you're like, here's the internal types, I can make these safe Rust types, and here's the interface to the rest of my project, and that can be unsafe C interface. That works great.
Yeah, I think this goes to a very good, how do you call it, kind of question of when should I look at using C2Rust to change my existing C code to Rust, and when would I maybe just want to use that as kind of a guideline, maybe like really look at an end-to-end system, what comes in, what goes out, and then use that as my guideline and just rebuild everything from scratch with a new architecture in mind. I think you kind of touched on that because if I remember correctly, I don't think, what's it called? The Tor client, right, has just been rewritten, or at least a good part of it. I think they literally just rewrote it because at least one of the problems is that it's got tech debt. Years and years and years of serious tech debt is a good thing. I don't think they use C2Rust at all. It would be interesting to hear about any projects that did use C2Rust. Yeah.
Yeah. We've got a few projects that have let us know about how they've used it, and a few other projects that we just kind of find in the wild. But to your original question, though, tech debt matters, and projects that have a lot of it that have accumulated a lot of weirdness over the years and are not well structured, probably not the best candidates for an automated translation. You can always try it and see what it looks like. That's one of the nice things with that we're aiming for with C2Rust, is something that's easy to use. But you might end up with something where you're like, this still makes no sense. The structure is incomprehensible. We need to start over. The places that make the most sense are where you have detailed, say, fiddly logic. For example, parsing like audio video codecs, that kind of thing. Somebody's implemented the actual codec decoding or encoding. And that we're pretty sure is correct. We've, run it against a bunch of examples of the format, and it seems to do what it's supposed to do. So you don't really want to rewrite those things from scratch. You want to take those bodies of those functions and sort of go, okay, I want a starting point that is the same. I don't want to touch it at all. And then I'm going to touch the input and output of that function to say, okay, rather than taking in a pointer and a length, can I take in a slice of bytes and try to parse that slice of bytes into a structure? Well, probably. That's a pretty normal thing you do in Rust. And I don't have to touch the logic of the function at all. So things that have complex logic but are well structured besides that are the ideal thing, in my opinion. We've had good success with that. We've been translating, it's a little bit old by now, but we were translating the expat, EXPAT XML parser. It's a streaming XML parser where performance is sort of critical. And so we wanted to translate that into Rust and see what happens. And we got it. It's probably about 90% safe at this point, just through manual refactoring and work on it. It's a very side project for a couple of our folks, and it'll eventually get finished. But things like that, where you have detailed logic you have to preserve correctly and you have to preserve identically, is the important thing.
Yeah, that reminds me, there's too many. Like, I think a good example is we had on the show Arthur. Maybe I said his name wrong. It's still early for me. The creator of Hyper.
Yeah.
He talked about how the spec for HTTP is just like a lot of you should do this, but then there's things that don't happen like they should. So you have to handle all this weirdness. So I can imagine if this was written in C and it was done perfectly to where you had 99% or higher for stuff working, you would say, you know what? Like you said, that kind of codec, that translation, let's just port that over and then maybe just dress it up so it looks nicely. Even if it looks something alien, it works, right? Or at least we can check to make sure it works, and then just don't touch it.
At least we're starting from a point where we know it does the same thing. And so we can only break it so much from it already does the right thing. All of the tests already pass. That's another thing that sort of with incremental translation versus a complete from scratch rewrite, you're starting from a point where your tests pass. And that's important because now you have a starting point where if you make changes and the tests fail, you know you did something wrong and you broke it. Of course, not everything's going to catch in every test, but at least for projects that have good test suites or good ways to fuzz them, you're already starting from a working project. That was super important when we were working on expat, is pretty high confidence that if I'm changing some types somewhere, I'm not changing any logic anywhere, and the tests still pass, and the Rust compiler is happy with me, I did it right. Like, that's a huge thing. Versus if I had to start from scratch and parse XML and get this into the same exact format for interoperability with a web browser, for example, I'd need to write a lot of code in Rust before I could have an end-to-end working example that runs through the test suite.
Okay.
So it's sort of, there's pros and cons to both a from scratch rewrite, an incremental rewrite, if you will. It really comes down to if you're going to rewrite in Rust, which is a big question, you should figure that out first. But if you're going to rewrite in Rust, then you need to take a really hard look at, is the code I'm starting from good? Like, is this a good starting point? And how hard would it be to get it right in a from scratch rewrite? And if the answer is it's either a really good starting point, we're happy with the code as is, we just wanted a memory safe language, or it's going to be really hard to get all of the corner cases and all of the fiddly parts where we know this did the right thing before correct, then an incremental translation, even if you are working sort of one function or one module at a time, only doing a partial rewrite in Rust, you're probably better off there.
Now, something really cool, which I'm sure this is probably out of scope, but I would be surprised and happy if possible. We keep talking about, your tests, right? If there's a way that we can also translate the tests, I mean, I don't know what the testing situation in C looks like, but I'm guessing it's probably Wild Wild West where there's so many different frameworks. So, but if there's a way that you can translate some or at least one of the test packages over into Rust tests, that would be really interesting, but I'm not too sure how that would even work.
Yeah, good question. Doesn't necessarily work one to one. It depends on where you're starting from. For a lot of projects, your test suite is just more C code. And so you can translate your test suite into Rust just the same as everything else. And that lets you do nice things like cargo run test binary. And if that test binary runs, 50 tests, well, hey, you just have an easy way to run your test now. It's not cargo test, it's not integrated, but it's easy. You don't have to muck with a C build system or a test harness framework or something. For other things, it depends on how your tests are written. If your tests are written sort of in a one test is one function kind of thing, and you just have a wrapper around that that's a runner, then putting the test annotation on each one of those functions and then calling cargo test works fine. A lot of C test frameworks do sort of initialization and set up things before and after, or like before all of your tests. There, you're in a more complicated spot. Rust doesn't really have yet a good way to do setup for a test or a bunch of tests in a consistent way. This is something that it's sort of lacking, and there's some interesting work being done on custom test harness support in Rust. So I believe it's nightly only, but you can tell the Rust compiler, hello, I would like to write my own test harness that isn't the standard test runner, and I just want you to give me a list of things that have the test annotation. And then from that, your test runner can do whatever manual custom setup you want, then run all of your tests, and then report the results in the same way. So there's sort of steps being made in that direction, but it's hard to get that right because everybody has a sort of different requirements for their test framework and what they want. For example, if you use Google Test for C++, that's got a set of assumptions on how tests should be run. And do you want those in like those assumptions, or do you want a different test framework's assumptions embedded in the Rust library? And the answer is you probably don't want those assumptions embedded in the Rust library. You want those to be separate crates. So hopefully we'll get to the point someday where we can have test harness crates and you can pick your favorite and then just use that test harness crate as your setup and initialization and test runner. But we're not there yet.
Okay. Yeah, I mean, the project overall looks really cool. And you said you actually talked a couple of projects. Are there any projects that people maybe will know that's actually using C2Rust right now?
Yeah, I was going to try to look that up real quick. I should have looked this up beforehand, and I did not. So let me take a look and see if I can find that while we're talking. I don't know if you have.
Yeah. Other than that, I mean, I think I don't have any more questions on my side.
Fair enough. So I'm going to forget what project it was, which particular library. So one of the interesting things that we ran across somewhat recently, somebody told us about, the author, I believe it was a video codec in Firefox, pretty simple one. They ended up running through C2Rust, just sort of worked, and they just kind of used it. After cleaning up the types, of course. This is something that we just didn't hear about until recently because things kind of worked. There was another project called H3. It's a GIS system. We recently had somebody come over to our issue tracker on C2Rust, which I would highly recommend y'all visit and look at. And if you want to help out on any tasks, we always accept. We're happy to accept contributions and love the community. But they came in and gave us some feedback and asked for some things and some bug fixes. But they're using that to translate H3 into Rust and get an H3 library, which does hexagonal GIS, I think, which is super cool. And that's neat to see. That's probably a good spot to mention that, like, we have a little bit of an open source community. We would love to grow that community and have more folks helping out on the project. The GitHub is github.com/immunant, IMMUNANT /C2Rust 2. Or you can go to C2Rust.com and find us. There's links there. But come by the issue tracker, file bugs, help out. And most importantly, we'd like to see where people in the community are using this and what can be improved for those use cases. I know there's tons of usability and sort of readability things on the output Rust code that can be improved, and sort of prioritizing those is important. We're also working on improving the safety of the output Rust code. And that's an interesting research project. So this all started as sort of a research project to see, can we do this? And turns out the transpiler, yeah, we can do a transpiler. Might be a little ugly, but we can do it. Now, the interesting question we're tackling is, we've got unsafe Rust code. How safe can we make it automatically? Can we infer lifetimes and sort of figure out what the memory model the C programmer was envisioning in a somewhat automated fashion? Like, anything is better than nothing here. And remove some of that unsafe. Turn pointers into references. Turn allocations, malloc, into box. Like, is that a thing we can do automatically? The question is not just, is that a thing, but how much and how useful is that? So we're currently working on a project to do that. It's on our, open source stuff. You'll see a bunch of issues there and a bunch of branches that are discussing this stuff. And we're basically going for an approach where collecting dynamic information, sort of a profiling run of the program. You run your program over your inputs. It does whatever it does. We observe that, instrument it. And then from that sort of observations of how it actually ran, we're like, well, I can see that this here is an array. It's a growable array. This looks like a vector. Can we make this into a vec? Or, simpler example, we've got a pointer coming into a function. Is that mutably borrowed? Is it immutably borrowed? Can we just take an immutable borrow of this object that was coming into this function? Is it an array? Is it a single object? If it's an array, could it be made into a slice? These are all interesting questions that sort of at the fundamental level, they're undecidable. Like, for any program, yeah, we're not going to figure it out. But for some common cases, how far can we get? How much time can we save the programmer who's having to refactor all of this and make it safe? So our goal is to sort of minimize the number of unsafe lines in the program. There's still going to be some, but if we can get rid of, say, a quarter, half, I don't know, of your unsafe raw pointers, that's a substantial step towards making this easier for people to use. So that's currently where all our sort of effort and thought and research is going into.
Oh, that sounds good. Yeah, because a lot of people don't want to be working with unsafe Rust, right? What's the point of Rust if it's not safe?
Exactly. What's the point of getting to this Rust code when it's all unsafe? I think we were talking before we started recording the podcast, but this whole C2Rust project was a joint project between my company, Immunant, and another research company called Galois. And they've been great partners on this. You can see some of their blog posts on the project. And they're also helping us with making it safe thing, working together on sort of partnering on doing dynamic and static analysis together, marrying these two types of analyses into something that is more useful than either one by themselves. So a lot of folks over at Galois have helped out, and I just wanted to give out a big shout out to them. They're super great to work with, all those folks. So.
Okay, cool. Yeah, if there's nothing else, then I have no more question. I think you answered, I feel like I know a lot already about it, and I'm looking forward to getting a little bit more safe code generated would be great. That's huge.
Yeah, that's a big thing. I think we'll be having a blog post on the sort of safety project coming out soon. So you can watch our site or the Immunant blog for probably put out later this month. We're going to put out, or next month, sorry. It's not quite December yet. Put out in sometime in December, we're hoping to get out a blog post sort of describing that project in more detail and sort of looking at what our goals are there, how we're going about it. But in the meantime, you can always go check out the transpiler. If you don't want to cargo install C2Rust, you can always run it on the website. There's C2Rust.com. You can run a little web tool that translates C into Rust for simple examples. You paste your code in there, see what it looks like, see how ugly it is, come back to our GitHub and say, hey, this is really ugly, but this little bit can be improved, and we'll point you where you might be able to improve it.
Cool. Okay. And with that, thank you for your time. And maybe we'll have you back to talk about this other project. It seems really interesting.
Yeah, thank you, Ellen.
I'd love to hear
It's been a
about how
lot of
you
fun.
translate to say for us. That's tricky.
I'd love to hear about it too, so we'll report back in when we can, maybe later.
That's good.
Thank you.
Thanks again.
It's been a blast.